Hello and good morning to my talk. I really appreciate that you got up so early. I mean, it's Sunday, 10 o'clock, and I do know myself very well how hard it can be for computer people to get up that early and even on a Sunday. So thank you all for being here and welcome to my talk. There at the top is understanding operating systems. So the first half is general operating system concepts, and programming a Linux kernel is another half about concrete Linux kernel source code. And we'll have a practical part where you will be able to choose which thing you would like to see closer later. You also might notice that this screen is not exactly the same as this screen. That is because graphic design is my passion, or like not, I'm not good. It's a part in that I'm generally not good at making good slides or pretty slides, and also I don't care that much, so be warned. Okay, so why? Why did I decide to give this talk, and why do I care about these things? I do deeply believe that to be a good programmer, you do need to understand your operating system, because usually the whole system, the whole solution you are giving to your user or to your customer, if you do it commercially, will always contain an operating system. And usually, like, the operating system is like 90% or 95% of the whole thing that you deliver. And it is really important that your application works well with the operating system, because after all, it's just a process in the operating system. And if it doesn't, you can run into a lot of problems, like mostly performance problems, but sometimes even also reliability problems. So one practical example that I experienced once, I did help a company. They did embedded devices and a medical device, and they had the idea to, in this embedded thing, to do a microservice approach. So have like 60, 70 Linux processes that all send data to each other for their work and for a lot of their medical data via a Unix domain socket. And they did run into performance problems. Like, the thing had a pretty good processor, but still they very early already had 90% or 100% CPU load. And the problem is that when you have so many processors and they're all interacting on Linux, every time one processor sends data to another one, you have to copy the data from one process to the kernel space, then switch to the other process, and then copy the data from the kernel space to the other process. And they had it even worse. They had their own router process. So every interaction between two processes was like 1 copy, 2 copy to the router, 3 copies, 4 copies. And then the context switching also, like the Linux has to switch from one process to the router process to the other process to make this all work. So they very fast got performance problems. And this mainly was because the architect developing the software architecture did not really understand operating systems, and he has not seen my talk or something like that. And also, like, one solution to alleviate that problem would be to use shared memory instead of Unix domain socket. So stuff like that I will be explaining here. So every abstraction that an operating system provides you, or a library, or everything, is leaky. Abstractions are, by definition, unfortunately leaky, and you have to know what the abstraction is, what it abstracts away, and how good it works, and what are the boundaries to use it properly. Another example would be a network socket. So if you have a network socket, there's a TCP connection behind it, and the promise is that it's like a direct file you can just write to. But as we all know, network sockets, TCP connection, go over the network. Network is not reliable. So if you want to write a really good software that is reliable, you have to do some stuff yourself to provide that extra buffering or reliability. So that's what I'm meaning with leaky abstraction. And one other comparison that I thought of is socialism did not work because it ignored the reality of human psychology. And the same is, if your software ignores the reality of hardware and operating system, it might work for small cases, but it won't scale and it won't get big. And so that's the same. So I'm trying to explain some of the underlying reality things. Of course, I cannot cover everything in 2 hours, but the things that I think are most important. So who am I? I'm the guy from Germany. I'm very thankful for Installfest for inviting me. I'm of course, embedded Linux kernel developer. I'm also kind of an academic, so I'm still doing my PhD in like combined work university thing. I've been gaming on Linux. That's mostly there because I've used this slide also for my talk yesterday. That was about gaming on Linux, so the line is there. Even out. So the next point about me is I like anime. So that was the private thing. So in general, when you talk about Linux kernel development, one of the more important topics I already mentioned is processes. Like, what is the process model of your operating system? Because the process is where your software lives in, and I will explain that a bit. That also includes scheduling decisions, it includes preemption and also sleeping, because most of your programs usually sleep most of the time. So when a program waits for input from your keyboard, or it waits for input from network or from hard drive, it's usually sleeping. And the operating system is doing stuff, or other programs are doing stuff. So this whole process of making processes sleep and wake them up again, I will talk about it a bit one. And also about system calls. File systems are also a service that usually the operating system provides for you. So the thing is, hard drives or also SSDs are quite primitive devices. So to have something like a file in a folder that also has like permissions and an owner and stuff, the operating system does a lot for you. And also to have that fast. So there's buffering and all that, which is pretty important. Memory management, the thing is, usually for your process, it looks like it has its own sandbox where it can do stuff. So every process thinks all the memory belongs to him, which is nice for the process and makes the job of the application developer much easier. But this is also a simulation that the operating system does provide for you, which is pretty helpful. And how that is done, we will also cover a bit, but it's not the main focus here. Networking. This is also a service the operating system does provide to you, usually, which is pretty cool. And actually, to make network connections work reliable is a lot of effort. It's actually part of my PhD thesis. And TCP does a lot of quite smart magic, and it just works for you, which is cool. We should also mention that the file system and also the network part, these are things, they don't necessarily have to be in the kernel. There is also the concept called microkernel, where the kernel only does the very basic scheduling and process thing, and all these other extra services are provided by other processes. Minix is a good example, QNX is one, and I think one experimental system by Microsoft also did that a lot. So this stuff doesn't have to be in the kernel space, but it can. But I will also explain more in detail what kernel space actually means for you. So what do we have more? Interrupts, I already covered them. And locking, you do know locking from user space already, usually, your semaphores and logs for some critical area. It is actually the same in the kernel. You also have to take care of locking, maybe even more, because the whole Linux kernel is multi-threaded. But we also do have to make locks work for you, for user space, because locking can also mean if one process or thread wants to access something and it doesn't get it, it will be sent to sleep. And this whole sleeping thing is then again a scheduling thing, where a scheduler has to know, okay, it has to know, for one, I have to send this process to sleeping, but it has also to know when to wake it up again. So when this resource becomes unlocked, that he later will put it in the runnable queue again with some priority. So that's something why it's important for the operating system. And so far about the topics. Now an overview of the talk here. We do have this knowledge part I told you about, and we do have a doing part. And the knowledge part will be longer, and in the doing part also you can vote what I will do, and you can watch me doing stuff and explaining stuff. And the stuff, it starts very generic, so for all operating system, Windows and also Apple too, and it gets more and more Linux specific over time. So we have a lot of the general stuff, we have system calls and scheduling, I will also explain interrupts, and also a little bit, only 2 slides about virtual memory. That's mostly time reason, like I had to decide, and I find virtual memory not as fascinating as interrupts. So that's why I decided this way. So, what are good sources? Which I based on, and also I generally like reading, and I have mentioned here the Comet book that is worth actually Googling. Let me check if, here is my browser. So if I just Google Comet book, maybe I have to add operating systems too, actually. Yeah, you get, I will show the commercial one here, a link to this one. So this is actually an open source book, but I would recover getting it in print. And it explains the operating system stuff, but what is cool about this one is that it has a lot of examples from the Linux kernel. So it usually just explains the concept, and then here's the source code in the Linux kernel that does that thing. So that is a really cool book. It's quite up to date. So that is my primary recommendation for today, I would say. But of course there are other books. There's also the dinosaur book. It is called, I think, Operating System Concepts from Silberschatz, which is also goodish, but it's quite theoretic. So if you just get one book, get the Comet book. There are also books from Starlings and Tannenbaum that are pretty cool. What is nice about the Tannenbaum book is that it also has a big part about all the concepts. And then later in the back, it has a part where they say, how does Linux all the concepts we explained, but then also how does Windows all the concepts we explained, and how does Android it, and I think also how does Apple it. So they also did a very good combination of practice and theory. This is a book where I learned most. It's also very source near, but it's also very old. So I would not recommend it anymore. It is kind of there because I did these slides 5 years ago and then updated them, and I did choose to let it in. So if you get it very cheap, you can get it, but it's only a small recommendation. And also, in the Linux kernel source code, there's actually the unreliable guide to hacking the Linux kernel, which is also worth a read, and it's free. And if you cloned your repo, you get it too. And they also do explain the whole locking and interrupt stuff pretty good. So, finally we get to the process thingy. So I have included a very good editor as an arbitrary example here. So here you have a process running, here you have your OS code, and here you have all the hardware. And the reason why I did it draw like this is because 90% of your application code runs directly on CPU and RAM. So it's not that there is here your application and then there's the operating system and then there's the hardware. It's not that everything has to go to the operating system. It's wrong. Most of your code runs directly on the CPU. And only if your program needs something that requires a bit more privileges or some of all these special services, it will have to ask the operating system. So if it wants to open a file, it has to ask. If it wants to write to a file, read, and also if it wants to do network stuff. But the whole calculation stuff goes directly, which is pretty nice for performance. It is called limited direct execution. And one nice example I've read in the comment book for this is also, it's a bit like children in a children room. So like the whole computer is the room, and then the operating system prepares the room so it's child safe. And then it lets the child play in there and do stuff in the room, but the parents are always in the background, kind of watching. And when the kid wants something that it should not just always get, like some cookies from jar up there or some food or something, the kid has to ask the operating system with a syscall. But also if some stuff comes from outside, like post office employees or people ringing at the door, that is stuff the operating system should take care of and not the child. So that is this limited direct execution, which is quite cool, and also it does work because the hardware nowadays does support it. We should add that too. So the CPU does know if it's currently in user mode or in kernel mode. There is an eFlex register in the CPU, and that does help in actually implementing that. So now we will get a few things about these system calls. So when the kid is asking the parents for something, so we have the application there, and most of the system calls go to a library that's the libc, usually the GNU libc, and the box you see down there, that's the kernel. There is a general system call interface, and then we have all the different subsystems of the kernel for handling different system calls. Then we have architecture-dependent code. So the Linux kernel is very modular, and you have those independent parts, and you have these architecture-dependent parts, and when you compile your kernel, you can tell him what architecture you want it for, and the whole set of make files and shell scripts you have there makes that happen. And the modules are here because it's not only modular in a build way, it's also modular in a way that when you have the Linux kernel running, usually the kernel binary is just a few megabytes. It's running in the boot directory. It's VM Linux, usually called. But that's not all the code you need. A lot of the code you actually need is in the kernel modules that are dynamically loaded when needed. And via this, hardware is very different, and computers are very different, and users are very different, and it would be quite complicated if you had one huge binary blob for every user. So it is more flexible to have one super small kernel and then have all the modules loaded on demand. So that's one of the reasons why we're using kernel modules heavily. Okay, so much about this diagram. This is more or less the same with other colors. You have your system call interface too. You have different subsystems. You have a memory management system I explained before. You have your process management. You have I/O. Sockets I explained before. File systems are a bit special insofar that they actually have way more abstraction layers than the others, because like you have all these block device, and then you also have the driver, and maybe even driver for your SATA controller, and a lot of more stuff. And also sometimes if you have pseudo terminals, the PTI device stuff is also in the kernel. Okay. So what do we more? So how is it with multiple cores, this whole kernel user space thing that I explained before? I do have an example here. So if you assume 4 cores, you see it's old, like nowadays 6 or 8 would be more realistic. You can have on CPU 0, your Firefox running in user mode. And on CPU 1, that is currently in kernel mode and doing file system stuff. And CPU 2 is just doing nothing. And number 3 is handling an interrupt from the network card. So that's perfectly realistic. So all the CPUs can do their stuff independently and switch back and forth before kernel and user mode. This is actually quite an improvement. Like 20, 25 years ago, there was one big kernel lock that only one processor could be in kernel, and when he had this lock, no one else could do kernel stuff. But when they realized multiprocessors are a thing, Linux was, okay, we have to develop, and then they started to introduce way more fine-grained locking for every data structure and every socket. And so to make this work, and this now working for like 20 years like that. So user mode versus kernel mode. So I have used them a few times. I should explain them, I guess. So code in user mode cannot do much. So like when you remember that square diagram before, you can execute your CPU code and you can access memory, but you cannot allocate memory. So if you want more, you have to ask the kernel already. You can only use the stuff that you're given, and also for interaction with hardware, there's often memory mapped I/O, so very special memory addresses, and user processes usually are not allowed to use them. And also user processes usually only get a limited time slice, and if that's run off, the kernel says, you go to sleep now, little child. Next child is allowed to play now. So that are important parts about user mode. And kernel mode, you may do everything. It should be added that this does even apply to user mode to root users. Even root users are still allowed to do way less than the kernel. Because the root, non-root is more like a privacy, security, and maybe system management distinction. But this is a very technical distinction. Yeah. So what more? Usually, so if you are on x86, you have the rings that help implement that. So kernel code usually runs in ring 0 or ring 1, and I think usual application code runs in ring 3. But it differs a bit, and this also depends on if you use virtualization or not, because your VM hypervisor might also use one of these rings. And I did not learn them by heart which ring is which one, But the important takeaway is Linux uses such hardware things if it can to realize its separation. So what do we have? So how do we transition between these modes? So there are special assembler instructions for that. They are pretty cheap. So just the moving is not that expensive. And there are system calls that just do move quickly into kernel mode and return. Stuff like get sock opt, so to get the option of a socket, or I think get time of day was one, maybe also get host name. So if you just go once to a kernel mode and back, that's usually quick. The expensive stuff is if you copy data and if you switch to another process or so. So the context switches are the very expensive things, just the mode transitions are okay-ish. Okay, so yeah, and some examples. From user mode to kernel mode, you usually go for a syscall, and from kernel mode to user mode, you go when you return from a syscall, or when a process was preempted because it ran out of time, but then later we have some time again. That would also be a reason to return. And also, I want to stress, all the stuff I've explained so far is the same for Windows 2 and for Mac. So, devices and interrupts. Oh, dirty. I did mention that because I noticed in a lot of university courses, interrupts are usually only covered very shortly. And I think part of that is because, yeah, they are dirty actually. As in, they do not fit in a nice, clean, high-level sequential model of your code or of your architecture. Because the thing is, an interrupt is if your hardware wants something and you have to do it now. No matter what you're doing, no matter if atomic or not, or your operation, you have to handle interrupts now, now, now. And it's a very hardware close thing where you have to also take care of a lot of quite hardware specific things. But it is extremely important in reality. I will give you some examples later, but just some terms. A very common short term for interrupt is also IRQ. And then interrupts have lines, like you have an interrupt on line 5, on line 12, on line 17. They're also called IRQ line. And then for every interrupt, you need a handler. That's a function. Usually it's a C function that takes care of that interrupt. That is usually called the interrupt service routine, so the ISR. And I will explain them a bit more detail later. So things that send interrupts. Mouse. Whenever you move your mouse, you send an interrupt. Whenever you click it, you send an interrupt. And every time your computer switches from whatever program you have there into kernel mode, handles the interrupt, and switches back again. And the thing that it works so fast, because processors are so fast that you don't notice it, which is pretty cool. Keyboard, every keyboard press you do. Your network card too. And also HD or SSD is a question mark because there's an DMA controller. Like SSDs have the feature that you can just say an SSD like, please dump the 1 megabyte that is there into RAM and notice me when you're done. And then the CPU doesn't have to do anything, but the DMA controller does that thing. And then when he's done, he sends the CPU an interrupt. This stuff is extremely important for performance. Otherwise, your computer would be super slow. Yeah. USB devices also send lots of interrupts on, yeah, hardware. That's actually German, unfortunately, yeah. I want to show you proc interrupts. So that is a file. So proc is generally a virtual file system that your kernel provides that contains a lot of things. Jawohl. And if we go here, we can go to proc. And to give you some examples, you can see CPU info here, which tells you a lot about your current CPU, but we are concerned about the interrupts file. And I feel a bit bad now for using Vim, but it is what it is. So here you can see my, here I have like 8 CPU cores. And these on the left are the interrupt numbers. So I do have an interrupt controller with lots of lines. And on number 1, I have this device. I honestly have no idea what it is. But on 8, we have RTC0, which is the clock in my notebook. That's important when I shut it off and on again, that my notebook still knows what time it is. Here we have RCPE. I do think this might be the keyboard, actually, but I'm not sure. So some of these numbers are fixed, but not all, so you can go more down. But now the important question is, how does the kernel know? Like, how does it know that on 8 is my RTC0, or that on 128 is the Thunderbolt connector of my notebook? Because that is pretty important to know what ISR, interrupt service routine, and also what driver stuff to call to actually make my Thunderbolt connection work. And because the ISR does very, very little stuff, it has to run very fast, but it does prepare some stuff that then more driver code will run later of the right driver. And to have this connection work, the answer is, it depends. So on normal computers like this one, for PCE devices and for USB devices, they are discoverable. So discoverable means if you boot, your kernel once asks every hardware device, who are you? And then some PCI Express card says, I'm the PCI Express card of this and this vendor. I have that name, I have that features, and I want interrupt line 128. So the PCI Express card that implements Thunderbolt for me has said that during booting. And it also says some magic string that the kernel internally uses for the driver matching. So we have this matching loop, and then during boot, it loads the right kernel model for the driver, and also it sets up this table and this connection between an interrupt 128 and that specific interrupt handler. And that is actually the main reason why booting takes so long, because your kernel does that for like every little device. He has to walk through everything on USB, everything on PCI, and does all that thing. So the big advantage is you can just dynamically plug in new cards and new stuff. The big disadvantage is it takes time, and it takes time every boot. So another way to do this that is very relevant for the embedded world are device trees. So those are files that contain all this information that say on your, usually you don't have PCI in a little embedded device, there you have SPI, for example. And that says on your SPI bus, on that and that address, you have that thing, and it runs with interrupt line 7. And it needs that and that driver. And the big advantage is if you have these things, booting is super fast because it's just there. The kernel has just to read this file. The big disadvantage is you cannot really change the hardware. You cannot dynamically plug in anything. Or you have to do extra stuff for do that. And also someone has to write these device trees. So they are text files that you can convert to code, but nevertheless, someone has to do it. And that also means someone can mess it up. Okay, so much for this little example. So to go back, what more do we have? Here we also have a graphical thingy. Interrupt comes from the network card. Now I want to explain the difference between preemption and interrupts. So interrupts I've already explained. So from the hardware, and very hard, you have to handle them instantly. Preemption is when a user space process is made to sleep, to run another process usually. So that is way friendlier, and that's also something that your operating system has a lot of more control about. So if you have to do some locking stuff, you can finish that first and then lie the one to sleep. And usually a process gets preempted if either it has run out of its time slice, or if some other way more important process becomes runnable again. So the important part is like preemption is more a process and a more high-level thing, and interrupt is more a hardware and low-level thing. We will see this divide between the process world, where stuff are more regulated and cleaner, and the interrupt world a few more times later, which is kind of important for kernel development stuff. So I have explained interrupts so far, but there is sometimes some confusion because there are also exceptions. So what is an exception? That is something that comes from inside the CPU. Like if you divide by 0, you shouldn't do that, that's wrong. And then you get a CPU exception that also traps into the kernel, and also the kernel then decides what do we do with this nasty program that just divided by 0. And you could configure your kernel so that it kills every program that divides by 0. It's not a default, but if you want to be mean, you could do that, for example. Other, a bit more serious exceptions are also page faults. So if your program wants to access some memory address that it has not done malloc for yet, that's also an exception. And the main difference is, like, the exceptions, they are nicer to your processor, they are less disturbing. Like, you do have in your processor your pipeline of instructions to handle, and with reordering and all the stuff, and if you have an interrupt, the processor has just to throw away everything and do the interrupt. But when there's an exception, you already kind of know beforehand which instructions can produce exceptions, which not, and you can handle them so that they produce less performance impact. But still, they are kind of comparable, that both are things that you have to handle quickly, and both are things where you jump into the operating system. And often, especially in older systems, you had like one interrupt vector, like one central table with all the interrupt numbers and then the addresses of the functions to handle. And usually you use the same table for the interrupts and for the exceptions, because they're kind of similar from the handling perspective. So that's why they're often explained together. But for the CPU, for the hardware, it's different things. And also, please note, those don't have anything to do with like C++ exceptions or Java exceptions. It's just the same term for very different things, actually. And you can do, I will show that quickly, because that is interesting. For this stuff, you can read the manuals of your CPU provider. So there is one 133. Can you see that? One pretty good book that is also worth a look. But I will first show you the cover. And then this part here. So that is the cover, Understanding the Linux Kernel. It is pretty old, so you usually get it very cheap on Amazon, or I got my copy actually when my library sorted it out. But most of the stuff is still accurate. And it is quite an interesting background read. Also for the thing that I explained before, so it was page 133. So here the interrupts and exceptions. Let's also close this here. So interrupts have two chapters that are the maskable and the non-maskable. We will explain this masking later. The thing is, the non-maskable are the super important that I cannot ignore under any reasons, and these I can ignore sometimes. And then the exceptions are everything inside processor, and you can also divide them further. I think the difference is with a fault. If you have a fault during an operation, you handle it, then you go back, and then you do the operation again. And I think with the trap is, you have a trap, you handle something in the operating system, you go back, but then you don't do it again, but you do the next instruction. There are also aborts, and what I wanted to explain you, there are also like these, they call it programmed exceptions in the Intel manual. So these terms are also from the Intel official manual for their processors. But the thing is, programmed exceptions are, example, what you use for system calls, or also for the mode transitions that I explained before. Some people call them software interrupts, but I don't like that term. I think exception or programmed exception is better there. So I wanted to show you that. And now, back to the slides. We do have, we have this, process context versus interrupt context. So usually your operating system, also if you have kernel code, runs in process context. And if you have user code also in process context, that means the kernel always knows I have a specific process scheduled that is responsible for the stuff. This is a bit like if you've ever worked in first level support, that you need a ticket for everything. So that's your ticket that you associate your current work with, is your process. And then there is the interrupt context. And the thing is, you have to be so extremely fast to switch from this one to this one that you do not switch to a specific interrupt ticket, but you just switch to void. For example, the interrupt context does have its own stack. And there are a lot of things you are not allowed to do in interrupt context. For example, in process context, you are allowed to sleep and put your process to sleep to do something else. In interrupt context, you cannot sleep, because when in interrupt context, your computer would sleep, like everything would just block, and you could not use your computer again. So that is like the most important difference, that you cannot sleep. And yeah, here's a bit more explanation. In interrupt context, you may not sleep, and you should there be very, very shortly, and also you only have a small stack, so you should not do any recursive programming in interrupt context. And also, I'm not sure if that's still true and if it's true on any architecture, but for a very long time, and usually, you cannot do any floating point arithmetics in interrupt context. You have only integer, basically. Yeah, your own stack. And it's kinda independent, but you still have the last process mapped, because you always have virtual memory, and usually the process that has been interrupted is mapped, but a good interrupt handler does not touch that and should never touch that. But theoretically, if you have some rootkit or some evil virus, it could destroy the one process it has interrupted. And process context there, and I'm sorry for the German here. In process context, you may sleep. It's like a bit the opposite. You have your PID, it's schedulable, and you don't have to stress. So at least compared to interrupt context, you can do slow stuff here. And now, so this is important, because you might be a bit confused. I did explain user mode and kernel mode before, and now I have process context and interrupt context. So how do they go together? And actually, you can have most of the combinations. So if you are in process context and in user mode, that's your normal process. If you are in process context and in kernel mode, that's your normal kernel work. So where you usually want to be, that is when you handle syscalls. They are called kernel threads, that are just normal processes that do not have a user part. They only have a kernel mode part. I think a lot of when your file system is doing work in the background, for example, X3 journaling is in one of these kernel threads. That is the main part of the kernel work, and usually the preferred one. So if you want to get your patches into the Linux kernel, you should try to have it run in this mode. That's the one that they usually accept. So yeah, then interrupt context and user mode does not exist. So you have to be in kernel mode to process interrupts. And interrupt context and kernel mode is the interrupt handler. Yeah, so much about that. And this, let me think a little bit. I do know that the stuff is also the same for QNX, because I did a little bit of QNX coding once. And yes, it is also the same for Windows, that you have your interrupt kernel handlers and have to be careful there too. So now a bit more about the system calls, the softer way to get into the kernel and to get kernel code executing. So here we have an example in a Firefox. First, you have your system call is still a for you it looks like a normal library call. You have malloc here. Internal in the C library, it sometimes does another call. Here it's brk. Then there may be another library because stuff is complicated. And then you get into the kernel. And the kernel can return to Firefox, but it can also realize while it does kernel stuff, oh wait, Firefox is already over its time, or another process that is way more important wants to run and then not return to Firefox. That might happen to your process. So you never notice for sure, but also usually you won't notice. So this is actually the same just with Vim and with another system call. And here we have, again, this distinction between user and kernel space. And here we do have a case where we go back directly, but that's not always the case. And this is maybe worth explaining the sysread. You saw before in a slide this SCI, the system call interface. So on the kernel side, all these calls are usually starting with sys underscore something, something, something. But it can block. That was my point here. So that is basically another example of what I explained. So you can go into the user space and the kernel space, and then the kernel says, I will run another process that might do his stuff, and then later, when it goes into a kernel, there we get the scheduler again, and then we got process A. So that is the preferred way and the usual way, that you switch processes when one process does a syscall. But it can happen when a process runs very, very long, that also he gets really preempted by the kernel too. So it depends on whether how cooperative a process is or not. This is worth mentioning because there was a time when people believed all processes will be very cooperative and we do not need real preemption. We just need nice processes. For example, the old Apple Mac 9 operating system had cooperative scheduling, so it did depend on every process giving back control to the kernel sooner or later, which of course didn't work out because even if the application programmers are nice, if they mess something up and are in some endless loop somewhere, you have the whole system hanging. So you do not want that. You do want a kernel that is powerful enough to actually preempt the stuff. That's also why Apple basically dumped Mac OS 9 and started with Mac OS 10. It's actually not Hurt, but it is a microkernel approach. Okay. So now the context switches. So how do I switch from one process to another one? And you have to save the register and all the state of your process to make that work. And there are two mode transitions, like you go in kernel space and then you go back to the, not back, you go to the other process. And also, and that's one of the more important and expensive stuff, you also have a memory mapping switch. So that means you had the virtual memory illusion of one process and you switch to another illusion. And that is quite expensive, and it also means that all your caches cool down because the caching was relative to the virtual memory addresses of the first one, so it's useless now. And also the TLB, that's the translation looker side buffer, that's a cache that helps actually in resolving virtual memory addresses to physical addresses, which is also very important for performance. That also gets useless. It cools down if you switch to a new process. So that is why context switches are so extremely performance hungry. It's not the actual switch, it's more all these caches cooling down thing. And this was one of the reasons why I explained before this example with all these microservices, why this was such a performance problem. But also, it can be a problem if you use OpenVPN, for example, because OpenVPN works in user space. So every time you send some data through your OpenVPN terminal, it has to be copied first from your process into kernel space, because it's networking stuff. And then the kernel notices, oh, it's a TUN interface. And the kernel has to copy it back to OpenVPN into the user space. OpenVPN does stuff and then copies it back into the kernel space and then finally sends it. The main reason why I did it is because it's way easier to implement something like that in user space. And usually it works, but of course the performance will always be worse than a VPN daemon in kernel space. So if you've noticed, there's like WireGuard. WireGuard is fully in kernel space and has like way better performance for this reason. Okay, what do we have next? Let me see. There is also thread switch. Threads between two threads is of course a bit more expensive because at least you do have the same memory. Because threads share the virtual memory, so that is cheaper. So next I do have a specific piece of hardware. It's a system timer. It is different than the real-time clock that I showed you before. This is a thing that you can configure at booting, like how often should it send a little tick, 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 tick to your operating system. And usually the frequency is 250 hertz. So all 2.5 milliseconds, I think. This thing does tick. So while I explained it already was like 40, 50 times. And every time there is an interrupt, every time the kernel does handle it. And now the question is why. The main reason is you want something to get reliably into the Linux kernel. So when the kernel does handle this, it also does check, are all my processes behaving nicely? Are they still all in their time slices, or do I have to preempt someone? So this is something to reliably get into kernel space often enough to actually work. So the thing is, if you put this rate down, you can save some performance. You can configure it when you build your kernel. But the downtime is the whole maintenance quality that your kernel does for everything gets a bit worse. And it's also relevant for timekeeping. So there are some computers that do not have the real-time clock, and they use these ticks also for their internal timekeeping. So how long have I been awake? We say that the system timer fires. It's called a tick. And there's a variable that's called jiffies in the Linux kernel. It's a global variable that counts all the ticks we have had since booting. And that you can also use for your timekeeping if you have no real-time clock. And also all the internal timers use it. So you can, if you're coding a driver or something in a kernel, you can do, or better example, with a TCP socket. If you do TCP, there is always a timer, like I'm sending a packet and I want a reply that this packet really got to its destination. And so when TCP, and if it has not in some time, we have to send it again. So what TCP does is it does start a timer every time it sends the packet. And if the timer goes down, it checks if the packet has been acknowledged. And if it hasn't, then it will resend the packet, and it will also change its estimation. Like it will say, okay, this connection is obviously bad. I have to send a bit slower to be nice to the connection. So this is one example where you really do need timers. And these timers also need these jiffies, and they also depend on these ticks. So every time we get a tick from the system timer, we also go through with a loop through all our timers and see if one of them has actually fired. And we need to do that. So what do we have next? So we have these 250 hertz. And then we have another thing that is also relevant for Windows and for other operating systems, but they do call it differently. So I did explain before that the interrupt handler should run very, very quick, and then there's other work to do later. This other work is the bottom half, and the top half is the interrupt handler. Yeah, it's that basically. Sometimes the whole thing is called interrupt handling by some books, but most books call this just the interrupt handler and this the bottom half. Yeah. So I do have a nice diagram here. We have the interrupt, we have our top half, and then we have a bottom half that runs sometime later. We don't know for sure when, because it's not that time critical. So it could be that we have one interrupt handler, one interrupt handler, one interrupt handler, and only then the bottom halves start running. And it's important that it works like this, to have your system still reactive. And the important part is, so these run in interrupt context, and those run in the soft IRQ context. So I did omit that before, but it is a mix thing between user mode and kernel mode. I will explain what is so special about this, but half of bottom halves run in soft IRQ context. More about that very soon. And what is important here now is in interrupt context. Okay, now this thing, when you handle an interrupt, it could happen that you get interrupted by another interrupt, and that's bad. That shouldn't happen, because at least these things you should be able to finish. So what you can do is, like your processor can ask the hardware, okay, please do not interrupt me again, okay? Or at least on the same line. So when you're processing something from your Thunderbolt controller, you're asking, okay, please do not interrupt me again. And then the hardware does accept that, and that is the interrupts disabled on current line. You can also disable them on all lines, but usually it is common to only disable it on the current line. That's like good tone when you're a driver developer. And one little thing is, I just said you ask the hardware. Actually, there is one thing, it's a PIC, programmable interrupt controller. That is a thing between all your hardware and your processor, and this thing is the thing you can ask to actually disable the interrupts. That's also called the demasking interrupts, if you remember before from the book quote that I showed you. So most interrupts are maskable, but there are a few where the hardware manufacturer said they are so extremely important, you cannot mask them in no coincidence. That's the NMIs, the non-maskable interrupts. And usually when they come, you are very fucked anyways. So yeah. So so much about this interrupts disabling thing. And that's the important thing if you are in the soft IRQ context. You are still in interrupt context. So what I explained to you before about the 2 pages about the you may not sleep thing, that's still true. But you have your interrupts not disabled. So it's like a compromise between the 2 extremes that you sometimes need. And the best example is most network code runs in this soft IRQ context. So most TCP, UDP, or IP handling is in this medium urgent context, so to say. Okay, so about bottom halves. So these 2 are the ones that are more important, or more like what I just explained, that they run in the special soft IRQ context. Soft IRQs are like hard-coded. I think there are 8 or 16 for very specific things, and they always get called when your operating system returns from an interrupt handler. And technically, theoretically, you are allowed to add your own soft IRQ handler. It is possible to add something in that struct, but this book I mentioned before does explain it, but practically it's very, very unlikely that it will be accepted in the Linux kernel, because that's a very big fundamental thing, and most maintainers in the Linux kernel are like, we shouldn't add anything to that. So maybe some companies did that in their private code, but you shouldn't usually. So there are also tasklets, so you can add your own function to a tasklet and put that in some struct, and then it gets called. That they are pretty common, but the general trend in the Linux kernel is to get away from both of them and to use more these. And these are also bottom halves, so they also do the work of bottom halves, but they run in normal process context. So that's the important thing, and usually you can do that with the process context. So there are very few things that are fall in this specific urgent that they are not urgent enough for the direct interrupt handler, but so urgent that you cannot put them in a work queue. So that are very, very few. So those are the usual solutions you should use today. Especially the threaded IRQs are the new hot thing in the Linux kernel. And Windows and Mac has such things too, but I'm very sure they have different names. Yeah. So, memory management. As I said before, only pretty short. I already told you about virtual memory. If we go here, we have a layout. And that is very old actually, because it's assuming 32-bit, 4 gigabytes. And every process has its stack, he has its heap, and those BSS and data and text sections are specific to the ELF binary format. And for example, these are uninitialized stuff, those are strings, and that's like the main binary of your process. Stack and heap are what you are using when you're coding. Or well, when you're doing Java, you're not directly using malloc, but your constructors and implicit destructors are using the heap. And about this, this is an example why the slides are old. Does anyone know why? What's the issue with these? Ah, okay. No, that's not. It is okay on multiple CPUs, but this is something I decided to let it in because it's a good example that Linux does evolve and change when needed. That is something that got changed with Meltdown and Spectre. But first to explain it. So until a few years ago, it was normal that in your normal process, even the whole kernel code and all the kernel data structures were mounted into, mapped is the better word, mapped into your process memory. But when a normal user space code tried to access it, it got an error, an exception actually. Because you can do that on x86, that you have memory mapped, but you do not have the rights to access it. And the reason for this was that when you do a syscall and then you change into the kernel mode, you have everything already mapped and you can just do your kernel work. So it's way faster than if you had to map the kernel code in every time you do your context switch. So it was a great performance improvement, but it was also a security problem. So the Spectre and Meltdown actually used the fact that it was there to do stuff. Also, unfortunately, I don't know what exactly they did, but it was a problem that it was available, and they did find some ways to access parts that are security critical. So the Linux people did something that's called PTI, page table isolation, to actually remove that from here. And you can actually look if you have that enabled or not. I did that in preparation when I noticed this old slide. So we have our Can you read the font? Is it sized okay? Should I do it a bit bigger? Yeah, okay. Is that enough for? Okay, thank you. So you can look into your boot directory, and there we have the VM Linux. This is the actual kernel. So there are multiple ones, because usually on your normal Ubuntu or Debian you have multiple ones installed, but only one loaded. And we can check which one we've loaded. So I've currently loaded the 6.12. So this file here is also somewhere in my memory doing my kernel stuff. The Z here, VM Linux, instead of Linux, it is because it's compressed. So my bootloader had to uncompress it and then put it into my memory. So that's the Z. And what I do want to show you, the fun thing is when you, on your Debian or Ubuntu, install Linux kernel, it's just a package you can install like everything else. With the kernel, there also comes the config file. So this one. So this is the config with which this kernel had been built. And that's just a text file that I can open with Vim. Sometimes. So the question. Okay, so the question was why don't you use /proc/config? Because it is true in this virtual file system that I explained before, there often also the running kernel provides you its config because he also knows it. But the thing is, I think it's a Fedora thing. My Debian doesn't have that. We can look, actually. We can. I didn't use it for years. Okay, so I have tried it, and then here we had the answer. You can, when you compile it, configure it if it's there or not. And it seems that the standard Debian one does not include it. But it is a valid point. Theoretically, it could be modified. For now and for here, you have to trust me. I did not modify my config file here. Okay, I have to remember everything to repeat it for the online audience. So, okay. Yeah.
Like after the kernel package is installed, there's some program or script called to copy it there, and depends on your configuration. It might not be there. Like on my system, there is no config in the boot. Basically, there's nothing much in the boot. But as far as I know, on most systems I've seen, I think in userlib, if you are user merge, userlib modules, and then the kernel version, you have the kernel image from the package and the config from the package.
Okay, so I hope everyone heard it. So yeah, it is a bit distro dependent. I still kind of assume that most people are using Ubuntu or Debian, so I'm explaining that part. But yeah, you can have it elsewhere. The directory that she mentioned, the userlib one, we might see it later because also the modules are there. So this is an important directory for the stuff. But for now, I want to show you this relevant option for the PTI. So this is what one of these kernel config files looks like. The thing is, you should not edit them directly usually. So when you configure your kernel, you have a tool that's called make menu config that generates that files for you, that also takes care of dependencies and everything. But if you want to look just quickly if something is enabled or not, it is totally fine to look in there. And all these options here start with config. And so what I wanted to show you was the PTI one, and not preemption, not optimize. Of course, now we have like 10,000 stuff with PTI. There was, I think, a better way to... maybe it was when I directly search for Meltdown. No, spect. Yeah, here you have this mitigation spectra. And these are the options that do the important stuff that did change this. So this PTI, page table isolation, is a thing some time ago that did solve the security problem, but it also did bring a bit worse performance. And the thing is, you do need this mitigation only on older notebooks. Like I think if you have the Intel generation 11 and 12, they have fixed it in hardware. So you do not need that anymore. But I do fear that this is something so fundamental, you cannot put it in a module. So Ubuntu has to put it into the kernel, and they still just put it in there for everyone. So if you are really performance conscious, this is something you can actually improve a bit when you compile your own kernel. And I would assume it's the same for Fedora. I don't know how it's for NixOS, but it is something worth looking into. So this whole Spectre, PTI, page table isolation thing. So I found that curious to point out. So what do we have next? We have locking. I did already mention that before. So important there is in the kernel, you have the sleeping logs, the ones where you can sleep when you don't get the resource. They are usually called mutex or semaphore. That's just how they name them. That's not really a general science thing, but it is so in the Linux kernel. And the thing is, you can use the sleeping logs only if you are in process context. So that's that thing before. So if you are in interrupt context and you are using a sleeping log, you are doing a horrible, horrible sin, because then it will happen that your whole computer will freeze sooner or later. So yeah, and also all the logs that are available to user space are of course implemented with the sleeping logs from the kernel. So there is this system call, I think it's called futex, fast user text, mutex, that uses such a sleeping log. And one thing, okay, let's first explain the other ones. Yeah, mutex, semaphore. I called them awake logs, so spin logs. So those don't really go to sleep, they just go in a loop, busy waiting for like 10 cycles, 20 cycles, and then try again, and then busy wait, and then try again. So those are the ones that you have to use in interrupt handlers, basically, because there you aren't allowed to sleep, and you have to check very fast again. But ideally, you design all your stuff so that you don't have to use any logs in your interrupt handler, but sometimes it's unavoidable. Like one example that I remember is when you have your list of your work queue list with work queue things, and the only thing that the interrupt handler does is actually add a bit more work to this work queue, and then it finishes. But the thing is, there could be, and even if this work queue is specific for that driver, theoretically there could be another interrupt handler running on another core for the same network card, also adding something to that work queue, and then you already need locking. So you would have to protect this work queue with a spin lock. So that's like the most common example for something like that. And one thing, what is very common nowadays and pretty cool are hybrid locks. So this fast footex thing that I explained to you before that you get in user space, and I think also the normal mutexes in kernel space, they actually first are a spin lock and spin for like 50, 60 cycles, and then if it still is not available, only then they go to sleep. Because with a lot of simulation it was found out that actually very often in this first time that's already enough to just wait a little bit and then get it. So that is a nice improvement, but it's also something you can disable when you want, but you shouldn't. Hybrid locks are cool. Okay, so that is everything about the knowledge part. Now we have the doing part, and it's actually democracy time, because we have like 5 options what I will show you, and you can vote, but first I will explain them. The first one is how to get my patch into the Linux kernel. So that's about the mailing lists, the repos, and more the social and organizational stuff that I can tell you a bit about. That's A. Then B is walking through the Linux code with some examples. I do have to add that we have only a half an hour left, so we would get only through the directories and the rough structure, but I don't think we would get into any files deep really with half an hour. Then the C option would be configuring and compiling a kernel. The D option is more about kernel modules and drivers. That also involves the directory you told about. That is the whole, how does the kernel during booting pick the right driver, and how does it load, and how does this probing with hardware work, but also where do my kernel modules live, and what can I learn and know about them. And the last one would be a tour de sysfs and proc. So proc you've already seen. I could show you a few more important, interesting files there. And sysfs is a bit like that. It's also a virtual file system. But the difference is it's more specific for drivers, and it's more specific for hardware stuff and kernel objects. But there are some interesting things in there too. Okay, and
I have a question.
Yeah.
Which topic is your favorite?
Oh, that's nice. He asked me which topic is my favorite. I think A would be my favorite. Okay, because I just remembered I also have to plan in some time for questions, so like the 10 minutes, so we only have 20 minutes actually. So everyone would get 1 vote, and okay, who wants A? Okay, like 3 people, okay. Who wants B? Okay, 6 people, 7. Who wants C? Because you've all done that already, I guess. Okay, who wants D? Oh, that's a lot. Interesting, I would have guessed that. Okay, and who wants E? Okay, I mean, we do have a clear winner, it's D. So, some more about kernel modules. So, we already do have our terminal, you can all read it. So, if we check here, 2 people are leaving, I guess that wasn't their favorite option. Okay. Good, so my mouse is doing weird things, and it stopped. Okay, so for kernel modules, the most important is the directory. We had that before. User, share, and there we have modem. I'm a bit confused. Was it user share modules? Oh gosh, varlib. I'm sorry. That are stuff that I often mix up. So var are things that are allowed to change on the file system. Now that is. I can try that. Let me try. Background tint color. Gosh. It did nothing. I did think about like that font would be something that people would need, but I did not think of.
The blue on black in the light.
I do get that, yeah. What can we do about that? Always this silly practical. Like I did change this, but it didn't help. I might try another terminal, but for toggle background, that sounds. Ah, is that better?
White text and white background. Yeah, no, it will be white text and white background.
So the one. Okay, so.
It is better.
But still not good enough for you greedy people. No, now we have that again. Like, no. Gosh. So it seems this tint. Let me look if I have another. Do I have terminate? What is termit? Does that work? It looks kind of better. So we. Ha! Finally.
Change also foreground.
Yeah, I'm a slow old man. First the font color, and I do not like things where you have to click as you might. Okay, that is black already. Foreground black. Let's do a last apply. That does look nice. Yeah, okay. So one other way we can go, there is one command that's called lsmod. That means list all the kernel modules that I have currently loaded in my system right now. And that gives a lot, so I will pipe that to less, so we have it nicer. So here we have IVL DVM, that's something for Wi-Fi. We have SCTP. That is curious because that is a alternative to TCP that no one uses, and I don't know why I have that loaded, but for some reason Linux did think it has to load it. I have to correct myself, I do think telecom services use it in the background, but it's still weird on my notebook here. And here this NF stuff, for example, is, where's my mouse? Here, net filter stuff. And also here you have dependencies. So there is a dependency hierarchy, or a dependency tree between all these things. And what I wanted to try is also we can get, if we take this IVL DVM thing, we can also do mod info. We cannot because I'm not root. Oh gosh. So we can do mod info IVL DVM, and it does tell me a lot of stuff about this module. It also tells me that modules are signed, so this is important for security reasons. So all my kernel modules are signed from the Debian people. So the kernel running in my kernel space is usually clean, and at least Debian says, yeah, that's cool. And I did hope, here is also the path where we find these things. It seems they have moved it sometime. It's in lib modules. And then we have specific to my kernel version. Let's just go there. To lib modules. And there you have a lot of kernel versions. And it seems this notebook is so old. I even have a 3.16. But I do think that Debian does delete that from time to time. So it shouldn't be that bad. And now I did already forget which one we have. We have 6.12, so we can go into the 6.12 folder. And there we have some stuff that is worth talking about. So we have this kernel folder, that's where all the actual modules are living inside. And we also have this modules alias file. So that is kind of interesting because, and relevant, if we look there we have the file name of a specific kernel module, and there we have this long mod alias string for every file basically. And this mod alias actually tells you the supported hardware. So if you remember maybe your Windows time where sometimes you had to get Google drivers by like vendor ID and device ID, that stuff is also in there. So usually when this discoverable stuff I explained before, so when your hardware via PCI, the kernel probes it, and then the hardware says, I'm that and that, and I have these and these alias properties, then usually the kernel does some pattern matching. It does match what it gets from the hardware against these strings. And that is also something where UDEF comes into play. So usually the kernel does communicate the stuff he gets from the hardware to UDEF, and then UDEF calls modprobe with these things. And the interesting thing is this stuff works in user space now. And then modprobe actually goes through this file and looks for these strings and then does the match and then loads the correct C state. So the funny thing is people always think UDEF is super important, but most of the hard work is actually done by modprobe, by the kernel tools. UDEF is just there to, that's a bit mean to say just to absorb performance. It does some things sometimes, but this matching is actually done by modprobe and by these things. But then there's also what you should know. Well, there's like a binary version of this file, because I think modprobe uses the binary version for speed reasons. Then we have a list of all the kernel modules that are actually built in. So that is also something that basically the Debian kernel team did decide for me. What did they decide to build in? So maybe I should explain in general. When you compile your kernel for most of the features, you can decide, do you want them not at all? Do you want them as kernel module, or do you want them built into your kernel? And of course, built-in stuff is faster, but also it makes your kernel bigger, and you should like not put everything into the kernel, because that would be super slow. And we can look what we have in here. So there we have all the file names, and also here you can see it's .ko for kernel objects. So that's the files, and you see there's actually a lot of things that could be separate modules, but that the Debian team decided, nah, we put it in. It's interesting that they did put like virt.io is for KVM, hypervisor, virtual machines. They did put it in, although I don't need it. Like, I don't use any KVM on this machine, but I did decide that enough people use it. We also do have a lot of crypto in the kernel. That crypto is for, to some degree, for the whole module signature stuff, but it is also because, as I explained before, the kernel also supports crypto for VPN. So, for example, when you do your WireGuard, you use this crypto support in the kernel. And we also have, like, for example, CRC, cyclic redundancy check, so checksums for stuff, or zlib, because you always have zlib everywhere. So it is 191. So usually the word count -L on this is interesting, like how much you have integrated. But I would actually assume that the Arch Linux kernel is not that different, because all these standard desktop kernels need this stuff. So what else is worth showing there? Alia. Then there's again these aliases, but they are not that important usually. We have that again bin. We have mod info. We have then, that is important, the dependency list. It's more a list than a tree. So we do here set no wrap. See here, like for every module, what other modules does it depend on? And that is pretty important. If you sometimes you want to unload a module and reload it because it didn't work properly. For example, I have a routine. If my Wi-Fi doesn't work, I do unload all my Wi-Fi drivers and load them again. You can do that with modprobe-r, and modprobe is the command to load them. But their dependencies are important, so you have to take care of them. Or also that is relevant. So there is the tool modprobe to load stuff. For example, I could load now for PS2 mouse, like the super old mouse. If I have a module for that, I can load it. Now my notebook supports these old mice. There is also an older tool that's called insmod, but you shouldn't use that. So the difference is modprobe does take care of dependencies, insmod does not. So modprobe does read all these files here. There's one thing I did want to tell you about this whole, do you compile it in versus have it as module? I once was at a company where they had the thing that they started the device and then very early they needed to know if some button was pressed. That was a button where a user could choose if it's like an emergency or not. And they had the situation that the driver for this button was a module. So they had to wait for UDEF and everything to like go through all the devices, and then at some point it gets to that button and then it loads that module, and only then they get the info what the user pressed. And on that device, everything else was already loaded, like the C++ software of them was running and everything, and they still were waiting for UDEF to actually load that module. And this was like really time critical to have that early. So that was a case where it was really worth it to include that in the kernel. So they had like been weeks and months already optimizing their C++ code to get it faster, but only did a few milliseconds. And then I did look at the kernel configuration and look at some graphs of stuff happening from UDEF, and then change the kernel config to actually include this, and then got like 4 seconds faster. And this is like also one of these examples where it's really important to understand your underlying operating system. And also fits in there. So if you know your hardware and if you're doing embedded, I would recommend to include as much as you can statically linked in. Modules are more if you have changing hardware or stuff like here. Okay, so what else do we have? We have the dependencies, then we have a binary version. We have order. We have symbols. Honestly, I don't know myself what the symbols file is. We can look at it. I think that are functions that this module offers to other modules. Because it looks a lot like how the typical function names in the kernel look like. And this is like a public API, because often if you do a module, you have a lot of internal functions that you put static before, because in C, static is basically what is private in other languages. And you have only a few functions that are available from outside, and I think that's this here. And then there's also something, I think this whole thing is like exported kernel interfaces, and there's 2 versions of this whole API, and that depends if your kernel module is GNU GPL or not. Like if you are nice and also do your code GPL licensed, you are allowed to use the big interface. But if you are evil and doing your binary proprietary blob, you are only allowed to use the small interface. And I don't know which one this is. I could imagine that it's more the big, nice interface here. But that's also worth mentioning. Okay. So the updates folder is also relevant because that's where DKMS puts its stuff. So DKMS stands for Dynamic Kernel Module Service. So that's basically a tool. It's pretty well integrated with apt usually, where while you do install apt packages, it does compile some kernel modules specific for your hardware. Okay, so there was one, not a question, how do we call it, addition, that it actually does, it always compile for all kernel versions, which you can see here, might take some time on my system because this Debian is so old. But I do think Debian has some ways of knowing, because in some of these folders here there are kernel modules, and some of them it has been all deleted, and there it doesn't compile it. So I think it's all that are actually available, and not all that have ever been on my Debian. But yeah. That could be. So what he said was it looks into/boot, so for what kernels are available, and then builds it. So it is a bit, people are divided if this is good or bad. I will just state my opinion. I think DKMS is pretty cool because you get something that is, you get a bit of the Gentoo experience. You get something that is specific for your hardware, optimized and only with the stuff that you need. And the thing is, they often use DKMS for things that cannot really be provided statically, so that have where it's necessary. So here it's something that's very ThinkPad specific, you can see, and here there's something very RCPE specific. And one thing that's also relevant about, so it's pretty easy to deploy your own kernel modules with this. So I did once work for a notebook company, and they had the problem that audio was not working on the notebooks they sold. Like they sold them with Linux, and sound did not work. And I did find a patch to actually make sound work, but the problem was the people out there were actually using Ubuntu. Like we had a small own repo that they added with our stuff, but the main kernel that they had were Ubuntu. And we did talk a bit whether we should start to create our own kernel, but I'm very happy we didn't. And what we did then is like we did provide one specific kernel module because we were so happy that the sound stuff that was necessary was not in the main kernel, it was in a specific module. And the nice thing is that in this folder, if you here place a kernel module with the same name than an other kernel module that already exists, and that has been like also compiled like the same, then the kernel will use your module that you have here and not the provided one. So that was a pretty easy way to override this specific audio stuff without having to change the whole kernel. So that was pretty cool, and that is a very good use about this updates directory, and I think I also did actually do it via this DKMS thing. So it is pretty easy to, with DKMS, to also make your own Debian packages that just contain one kernel module. And it is also, so last sentence, it is also possible to build such modules even if you don't have the whole kernel source code. So there is a Debian or Ubuntu package that is like Linux, image, minus headers. And that only contains most of the header files, and the build system of the Linux kernel is like 100 megabytes or 200. And with that, you can build kernel modules for a specific kernel, or the people that you give your DKMS package can do that, which is pretty cool and pretty practical. Yeah. Okay, so much for kernel modules. We now have 10 minutes left. I think that's a good time to start questions. Yeah, I have no idea how it works with the microphone, but it seems to be solved already.
Okay, so when we talked about system calls before, you said that there are cases like date where the system call doesn't happen or it goes directly to the kernel. I always thought about system calls as an exceptions in the CPU where kernel code is run to switch the ring and so what is this about?
Okay, I think I don't have to repeat the question. So to answer that, the system call does happen. What I did mean is it is way cheaper than a context switch. It's just that. So you can really fast go in and go back, while when you compare that to like a write or a read, where you have to copy stuff and then also switch elsewhere, and so that takes long, but these go very fast. And there's also a little addition that I did leave out, but there is something called VDSO. There is a little bit of data that is actually can be shared between the kernel and the user space. So for some of the and the current time is an example of such data. So for these, there is really no real system call happening. For these, you can just read the shared data and go back. I don't know how many calls use that, but if it's just, yeah, here they say explain it, get time of day. There are some cases where you can even more optimize the simple calls with VDSO, and then there are really no system calls. Yeah. Okay.
Okay, then I may have another question. When we were talking about interrupts, and you said we only disable one interrupt line, so it can still happen that there's interrupt in an interrupt in an interrupt because there are multiple interrupt lines.
Yeah, that's called nested interrupts, and that can happen. And also, when we talk about it, a little addition. Other systems have interrupt priorities. So there is a system, and also usually the interrupt controller supports that. That's only interrupts with higher priorities are allowed to interrupt those with lower ones. This is also very important in real-time systems. I do think even Windows has it. Funnily, Linux doesn't. Linux has no interrupt priorities. I don't know why either. That is something one might. I could Google maybe. I just read it in a book and was like, okay, weird, and then read on for more stuff. But so yeah, that can happen in Linux. Yeah, I mean even in the others, when you have multiple interrupts with the same priority, you also can nest each others. It's also called nested interrupts. But these priorities can help a bit with that, at least. So I don't know why not use them. But it works in the end, so yeah.
Okay, thank you.
Yeah, you're welcome. So, any more questions? Yeah. I think he had one. Ah, no, okay. Okay, then we are actually.
So you showed that the DKMS service is the one that actually loads the modules, I think. I don't have that on my system. I have systemd modules load service. Is there any meaningful difference? Is this an alias or a different mechanism altogether?
I have no idea. I mean, that's not very professional to say, but I don't like systemd. I try to avoid it as much as I can. But I mean, you also should know your enemy, so that's a good point. It was systemd, and then how did it continue?
Systemd modules load with dashes.
Ah, I think that does a lot less. So that only does take, and I think I've seen that before, does take care of loading some modules. So there might be the case when you don't want to use the udev dynamic way of loading modules, and also you do not want the module is for some reason not built in, then you can just statically load it in a way that's still faster than the UDEF way. So when this service gets executed, he will just load modules that are in a list. So you can provide it here as a parameter, but there's also, I think, a file somewhere. Yeah, it's the modules load D. So if you go into etc modules load D, so the modules that are in here will get loaded by the service. So that's what that's for. Actually, it is like the same that we had before with our old init system. There we had etc modules, if you remember that. Do we have that still? Ah, nice. Yeah, that's some Debian backward compatibility. So etc modules was also like that. That was when we hit this v init, it was just executed by some script that did mod probe on that, which is basically the same as systemd does too. Maybe systemd does it in C, so it's a bit more performant. Maybe systemd does something complicated, high level, I don't know. So yeah, but it's basically the same thing.
Cool, thanks.
Yep, no problem. Lol, okay.
So I'm not sure if it's right what I'm talking about, but from my opinion, just as an opinion, a DKMS is completely optional, and if you don't need drivers which are built for DKMS, like NVIDIA, Broadcom, and some other stuff, you just don't need DKMS at all. And it only happens to be that Debian-based distributions like Ubuntu does have it by default. So if you don't need the DRBD and NVIDIA drivers and stuff, you just don't need DKMS at all. It's a package, completely optional. You can just apt remove DKMS probably, and it will work just fine. It's my opinion.
Yeah. This is a good point. I'm honestly not entirely sure. Like I before said, you get the Gentoo experience, but I also don't really know if you would need it for these two. Maybe you do, maybe you don't, but you are right. And I mean, all the other packages get it done too to provide you with pre-built binaries.
So as I understand it, then actually the systemd stuff is just more like maybe an optional way of doing it, not using UDEF. So you have UDEF or you have some systemd modules mechanism, which I don't know, and DKMS is completely independent from both of those.
Yeah, those are different things. Okay.
Oh.
Okay, so. But you were talking about DKMS before, with your first question.
No, the question was
yeah. Those are pretty different things, yeah. Okay. Good. We are pretty good in time, but do we have any more questions? Yeah. I think that one was actually even visible in the camera.
So you said that you sometimes need to unload and load your Wi-Fi driver.
Yeah.
So even with your skill and your ability, you have some problems you can fix if there are some. Because I had similar problem, and with my skill, I literally had to change my Wi-Fi card.
Yeah. Basically, yes.
Thank you.
You're welcome. Yeah. Okay, so thank you all for your time. It was a pretty nice experience. I wish you, I guess you will have lunch now, so good lunch, and enjoy the last day of the Installfest.